Hello, everyone. Welcome to VCIP training course. The subject of today's lesson is an introduction of TR-069 basic and related troubleshooting methods. This lesson is mainly divided into three parts. The first part is the basic introduction of TR-069. The second part introduces the TR-069 configuration on the VSOL device. And the third part describes the troubleshooting methods of common cases. After this lesson, you will be able to: Number 1. Understand the function and application scenarios of TR-069. Number 2. Understand the basic settings of TR-069. Number 3. Understand the common troubleshooting methods of TR-069. Now let's start with the first chapter. Traditional network management mainly relies on on-site access or users' self-configuration, which is inefficient and costly due to the popularity of a large number of network terminal devices. The configuration interfaces and methods of each device vary, posing significant difficulties for ISP management and maintenance. TR-069 provides a unified standard interface and management framework, allowing ISPs to remotely manage and configure users' CPE devices, such as home gateways, routers, etc., without on-site service, greatly reducing maintenance costs and improving efficiency. TR-069 is Technical Report 069, also known as Customer Premises Equipment Wide Area Network Management Protocol (CWMP), which is a standard remote management protocol between a CPE and Auto Configuration Server (ACS) developed by the Broadband Forum. It defines a mechanism that encompasses secure auto-configuration of a CPE and also incorporates other CPE management functions into a common framework. The application topology of TR-069 is shown on the screen. The Auto Configuration Server (ACS) is a key component in the TR-069 protocol framework. It is a network management system, usually operated by an ISP, Internet Service Provider, that is responsible for communicating with CPEs by southbound interface to enable remote management and automated configuration of these devices. The interface between the ACS and the management system is a northbound interface. The TR-069 protocol mainly defines the southbound interface. The TR-069 has several main functions. When the device is connected to the network for the first time, the TR-069 can be used to automatically configure settings such as VoIP, Wi-Fi parameters, and security settings, improving deployment efficiency and accuracy. The firmware of CPE devices is automatically detected and upgraded to ensure that the devices are up to date, reduce security risks, and improve service stability. A CS can adjust the configuration parameters of software modules, such as installation, uninstall, and update, to ensure that they operate correctly according to the needs of ISPs. The ACS collects device performance data, monitors network status, finds and resolves problems in a timely manner, and improves service quality. The TR-069 utilizes a multitude of existing, standard protocols to achieve broad device support. Employing these existing and widely utilized protocols can diminish the effort of developing TR-069 devices and enable TR-069 devices to integrate more seamlessly into existing networks. The TR-069 protocol stack is depicted in the figure, which is founded on the TCP or IP protocol. SSL or TLS is not compulsory and is employed to ensure certificate-based authentication between ACS and CPE. The message transfer between ACS and CPE employs HTTP 1.1, and the specific content of the message is encapsulated in a SOAP packet, which is an XML document encompassing a SOAP head and a SOAP body that encodes RPC using standard XML syntax. The remote management approach of ACS is to conduct remote invocations of the management functions on the CPE. The function name and parameters to be invoked need to be transmitted to the CPE. These contents are contained within the SOAP body. ACS does not make invocations directly to the interface of the device itself, but instead utilizes standard functions defined by TR-069, referred to as TR-069 RPC methods. Regarding the various custom applications on CPE and ACS, such as broadband, voice, and IPTV services, they do not constitute a part of the TR-069. The full name of SOAP is Simple Object Access Protocol, and its message structure is presented on the left. This course will merely cover the elements related to TR-069. A SOAP message is an ordinary XML document consisting of envelopes, header, body, and fault elements. Envelopes is the primary container of a SOAP message structure and the root element of a SOAP message. Every SOAP message must incorporate envelopes. The SOAP header is optional, and if one desires to add a header element, it must be the first child of the envelope, which itself can also contain 0 or more header child elements. The header element is mainly utilized for authentication. The body element in a SOAP message mainly comprises the methods of remote procedure calls and their parameters, as well as the data required by the target application. The SOAP fault element is employed to convey error and status information. If the fault element is included in the SOAP message, it must emerge as a child element of the body. The actual SOAP message captured using Wireshark is shown in the right figure. TR-069 specifies particular RPC methods on SOAP for configuration, query, diagnostics, and the like. In accordance with the initiator, there exist three types of methods: CPE methods, ACS methods, and generic methods. CPE methods are those initiated by the ACS and sent to the CPE. ACS methods are those initiated by the CPE and sent to the ACS. Generic methods are those that both the CPE and the ACS can initiate. Get RPC methods may be used by a CPE or ACS to discover the set of methods supported by the ACS or CPE it is in communication with. This list must include all the supported methods, both standard methods and vendor-specific methods. The receiver of the response must ignore any unrecognized methods. The CPE methods listed in this table are defined to be supported on a CPE device. Other optional methods are not listed here. In general, ACS can use these methods to obtain and configure CPE parameters. The ACS methods listed in this table are defined to be supported on an ACS. Only a CPE can call these methods. Other optional methods are also not listed here. The inform method is crucial. A CPE must call the inform method to initiate a transaction sequence whenever a session with an ACS is established. The inform message sent by the CPE to the ACS usually contains 6 arguments: device ID, event, max envelopes, current time, retry count, and parameter list. Device ID uniquely identifies a CPE. As shown in the packet structure on the right, it contains 4 parameters consisting of manufacturer, OUI, product class, and serial number. OUI is an organization unique identifier for the device manufacturer, represented as a 6 hexadecimal digit value. Product class is used to identify the product or class of product over which the serial number parameter is unique. Serial number is the identifier of the particular device that is unique for the indicated class of product and manufacturer. These values must remain fixed over the lifetime of the device, including across firmware updates. Any change would indicate that it is a new device. The event argument indicates the events that caused the session to be established. If one or more causes exist, the CPE must list all such causes. An event is an indication that something of interest has happened that requires the CPE to notify the ACS via an inform request. If the CPE establishes a session for which none of the standard event codes apply, then this array may be empty. The event struct entry in an inform message contains event code and command key, as shown in the figure on the right. Event code consists of an identifying character followed by a text description of the cause. The common event code and corresponding events are shown in the table. It is important to note that these are not all event types. In practical applications, we can use the value of event code to assist in troubleshooting. As for max envelopes argument in the inform message, it is set to a value of 1 because the protocol supports only a single envelope per message. And on reception, its value must be ignored. Its location in the inform message is shown on the right figure. The current time argument is the current date and time known to the CPE. This must be represented in the local time zone of the CPE and must include the local time zone offset from Universal Time Coordinated. The retry count argument is the number of prior times an attempt was made to retry this session. This must be 0 if and only if the previous session. It will be reset to 0 only when a session completes successfully. The parameter list argument contains multiple parameter value structs. Each parameter value struct instance consists of a pathname node and a value. Pathname node is defined by different types of data models. More on this would be introduced later in the course, but just know that it refers to the specific attribute parameters of the CPE. The screenshot of an inform packet on the right shows its structure. The data model is an essential component of TR-069. Through the definition of a series of standardized data models, the remote management and configuration of network devices are accomplished, significantly enhancing the efficiency and reliability of network management. It is a hierarchical set of parameters that define the managed objects accessible via TR-069 for a specific device or service and adheres to a common set of structural requirements. By the way, a vendor can extend the standardized data model with vendor-specific elements, parameters, objects, commands, events. Vendor-specific elements can be defined either in a separate naming hierarchy or within the standardized naming hierarchy. The screenshot on the right indicates the instance object name in the Internet Gateway device data model. In fact, the data model structure of the device is not defined in the standard TR-069, and different types of device data model structures are defined in other technical reports, such as the Internet Gateway device data model defined in TR-098. For example, the right is the screenshot of the configuration page of the TR-069 on the network device. The attributes of the TR-069 inform packet sending interval, ACS server address can be represented by the pathname node on the left. In TR-069, the CPE is always initiates a session. When making first contact with an ACS, how does it know the ACS URL it is supposed to contact? TR-069 defines the following mechanisms for discovering associated ACS. The CPE can be configured locally with the URL of the ACS. The CPE has its Bootstrap ACS pre-configured by factory default. This is usually the case with CPE that are deployed by a service provider. It may use if no other URL is provided to it. If the IP address of the CPE is obtained through DHCP, the CPE can obtain the ACS URL through DHCP option 43 sent by the service provider. Under the following conditions, the CPE must establish a connection to send to the ACS and issue the inform RPC method. The following figure shows the session flow initiated by the CPE. The CPE needs to establish TCP connection with the ACS first. If the ACS URL uses HTTPS, the CPE must establish an SSL or TLS connection with the ACS. The CPE sends an inform message to establish a CWMP connection. The event code field is used to describe the reason for sending inform packets. After receiving the inform packet and authenticating the CPE, the ACS replies an inform response packet, indicating that the CWMP connection is successfully established. If the CPE has no other request, it sends an empty message to meet the HTTP or HTTPS message request or response message interaction rules. After receiving an empty message, the ACS verifies the validity of the device according to the serial number in the message. If the verification passes, the ACS verifies the validity of the device. If the authentication fails, the ACS sends a message indicating the invalidity of the device. After verifying the validity of the serial number, the ACS sends a message requesting the CPE to report the account information. Once the message is received, the CPE transmits the account information configured on the local device. After receiving the message, the ACS verifies the validity of the message based on the account information. Only after the verification is successful can the ACS proceed with the subsequent process. The ACS sends an empty message to end the process. If the CPE is not authenticated using TLS, the ACS must authenticate the CPE using HTTP authentication. The CPE must support both HTTP basic and digest authentication schemes. The ACS chooses the authentication scheme by virtue of providing a basic or digest authentication challenge. If the CPE has received an authentication challenge from the ACS, either basic or digest, the CPE should send an authorization header in all subsequent HTTP requests for the duration of the TCP connection. Whether or not the CPE does this, the ACS may issue subsequent authentication challenges at any stage of the session within a single or multiple TCP connections. Use of an authentication challenge requires the initial message, usually an inform RPC method request, to be sent. In certain circumstances, if the ISP intends to convey configuration to the CPE via the ACS, the ACS is required to initiate a session and solicit the CPE to establish a connection to the ACS. Subsequently, the ACS dispatches an HTTP GET to the CPE. Once the message is received, the CPE employs digest authentication/shared secret to authenticate the ACS. In the event that the authentication is successful, the CPE establishes a connection with the ACS and transmits inform messages. The capture snapshots illustrate the HTTP GET process initiated by the ACS and the inform process of the CPE. It should be noted that if the CPE is situated behind a NAT or firewall, the ACS will encounter issues when initiating sessions, which pertains to intranet penetration. In the process of establishing the connection between ACS and CPE, all sessions must begin with an inform message from the CPE contained in the initial HTTP post. This serves to initiate the set of transactions and communicate the limitations of the CPE with regard to message encoding. The session ceases when both the ACS and CPE have no more requests to send and no responses remain due from either the ACS or the CPE. At such time, the CPE must close the connection. No more than one session between a CPE and its associated ACS can exist at a time. A session is intended to persist only as long as there are messages to be transferred in either direction. The LAN and WAN sides of routers in the topology belong to different network segments. The function of NAT is to map the IP addresses on the LAN side to the IP addresses on the WAN side. This means that if the ACS initiates the session flow first, it does not know how to forward the packet to the correct CPE because there is no related mapping entry in the router. To accommodate the ability for an ACS to issue the equivalent of a connection request to CPE allocated a private address through a NAT gateway that might not be CPE1 management protocol capable, the following is required. The CPE must be able to discover that its connection to the ACS is via a NAT gateway that has allocated a private IP address to the CPE. The CPE must be able to maintain an open NAT binding through which the ACS can send unsolicited packets. The CPE must be able to determine the public IP address and port associated with the open NAT binding and communicate this information to the ACS. When there is not enough public IP address available and NAT needs to be used, some protocols for NAT traversal need to be used to achieve management goals. STUN and XMPP are representative examples of such protocols. STUN, which full name is Session Traversal Utilities for NAT, is a protocol that addresses NAT traversal, providing tunnel modules with the means to ascertain whether a NAT device exists on the network and the IP address and port number assigned by the NAT device to the communication endpoint. STUN is based on UDP packets. The default port number is 3478. The ACS enables the use of STUN in the CPE if it is not already enabled by factory default and designates the STUN server for the CPE to use. The CPE uses STUN to determine whether or not the CPE is behind a NAT gateway with a private allocated address. If the CPE is behind a NAT gateway with a private allocated address, the CPE uses the procedures defined in STUN to discover the binding timeout. The CPE sends periodic STUN binding requests at a sufficient frequency to keep alive the NAT binding on which it listens for UDP connection requests. When the CPE determines the public IP address and port for the NAT binding on which it is listening for UDP connection requests, and whenever it subsequently changes, the CPE communicates this information to the ACS. Two means are provided by which the ACS, at its discretion, can obtain this information either from information provided in the STUN binding request messages themselves, or via notification on changes to the UDP connection request address parameter, which the CPE will update to include the public connection request address and port. Whenever the ACS wishes to establish a connection to the CPE, it can send a UDP connection request to the CPE to accommodate the broadest class of NAT gateways. This will be sent from the same source address and port as the STUN server. It is crucial to note that this course merely concentrates on the binding discovery process in protocol interactions. Other protocol particulars can be found in Attachment G of the TR069 definition document. Now, let's explore how CPEs discover their NAT mapping IP through stun. As depicted in the figure, the combination of IP and port is substituted by the notation AP. During this process, there are two significant messages: binding request and binding response. Once the stun function is activated, the CPE periodically transmits binding request messages to the designated stun server. If the CPE is pre-configured with stun username and password, the message will also carry the username and message integrity attributes. After receiving the message, the stun server responds with the binding response message. The mapped address attribute contains the source IP address and port information of the binding request message. Then CPE will inform messages through UDP connection request address instance will map the address and port information sent to the ACS. It can inform the ACS whether the NAT device exists through NAT detected instance. Then, let's start with Chapter 2. This chapter introduces how to configure TR069 on the vSol ONU and the function of each parameter. The TR069 configuration page on the vSol ONU web page is shown in the left figure. Different ONU models may have different web styles, but the configuration items are basically the same. Note that the URL of the ACS must be entered in accordance with the format requirements, and the username and password must be consistent with the configurations on the ACS. Otherwise, authentication fails. For the sessions initiated by the ACS, if certificate is enabled, the CPE can also enable authentication. The user can configure connect, request username and password. The configurations on the ACS must be consistent with those on the CPE. Apart from configuring TR069 on the ONU web, users can also remotely set TR069 parameters for vSol ONU through the vSol OLT. The configuration items are nearly the same as those on the ONU web. The selected project ID in the left image is applicable to the vSol INS server. vSol INS is a network management server program developed by vSol. Currently, the vSol INS server also integrates the TR069 service. Users can create their own projects under their own accounts on the server. Each project has a project ID, and CPE can fill in the project ID. When the session is authenticated successfully, the ONU is connected to the project that matches the ID for centralized management. The focus of this lesson is not on vSol INS, and it is not covered here. vSol ONU supports stun function. Users can configure stun on the ONU web or through OLT. The configuration items of both are the same. The stun username and password must be the same as those configured on the stun server. To communicate with the ACS, the CPE must have an IP address and a WAN connection. The WAN connection of the CPE must be set to the TR069 type. Then, the CPE can send inform packets to the ACS server. The left figure presents several fundamental configuration items on the ACS. In this case, the ACS is capable of configuring the username and password for authenticating the inform packets sent by the CPE and for initiating session connections by ACS. The username and password must be identical to those configured on the CPE. The ACS supports the configuration of URL for external connections. The CPE can establish a session with the ACS through this URL. Some ACS servers support stun function. By configuring the IP address of the stun server, the ACS can obtain the IP address and port number that can be utilized to access the CPE from the stun server, or even the ACS itself can act as the stun server. In Chapter 3, let's acquire some fundamental troubleshooting approaches and notions for TR069 related issues from several common cases. Snapshots of vSol ONU web configuration are used in the following cases. Case 1. What should we do when ONU fails to register with ACS server? Step 1. After setting up the ONU WAN, go to the TR069 inform interface for a manual inform. If the message is not inform success, it indicates the device fails to report the message to the server. Step 2. If it fails, use the ping tool on the diagnostics interface to check whether the ACS can be pinged. If the ping fails, check whether the device is working properly and whether the WAN connection obtains the IP. If the ping succeeds, check whether the WAN is of TR069 type. Step 3. If the ONU shows that it can successfully communicate with the server, but does not actually see the corresponding ONUSN on the server terminal interface, you should check whether the ONU is configured with the OUI and SN. Furthermore, you are required to mirror the ONU WAN side on the ONU LAN side, and then use the Wireshark to capture packets to view the interaction messages between the ONU and the server. Please refer to Lesson 1 of VCIP for the specific mirroring method of ONU. After mirroring and capturing packets are enabled, go to the ONU Web TR069 Inform interface and manually inform again. Then return to the Wireshark interface, enter XML to filter TR069 messages, ensure that the MAC of the packet are come from your ONU WAN MAC and from the ACS. Right-click on those packet and view detailed message interaction information. As shown in the figure, the red font is the inform message of the ONU. The OUI and serial number reported by the ONU can be viewed in the message. Please check whether the reported SN can be searched on ACS. If it cannot be found, check whether there are any restrictions on the ACS. Sometimes ONU can ping to the server, but the TR069 inform state shows inform break, and ONU cannot connect to ACS. We can also check by Wireshark after mirroring. This is a case of authentication failure. As shown in the figure, during the authentication interaction, the ACS sent a packet displaying 403 forbidden. This indicates that ACS rejected the inform request. The reason is that the username and password filled in ONU maybe do not match with the one on ACS. The solution to this problem is to check and correct the username and password you entered. Case 2. Sometimes the ONU has successfully connected to ACS. But when ACS gets or sets some parameters from the ONU, it cannot be set, or the wrong value is returned. This may be due to the ACS reading the wrong node, or the ONU might not respond correctly. We can still use Wireshark to check after the mirroring. This case shows that the ACS gets the Wi-Fi password of the ONU through this node, but has not received a response from that ONU. By analyzing the packets, we can find that the ONU replied to the ACS with a CWMP error code of 9005 packet, and by looking up the table, we can know the meaning, invalid arguments. That indicates the ONU does not support the parameters of this node. So for this case, you can read all the nodes of the ONU to find the correct node supported by the ONU, or ask technical supporter to help you find the correct node. We recommend that the ACS use this correct node to get the parameters. This is another case that the ACS cannot get the ONU PON RX power checked by Wireshark. If the VSOL technical supporter confirms that the server sent the correct node, but the ONU does not respond to the parameter value. This required VSOL engineers to release new firmware to solve such issues. Case 3. The stun-related issues. In the previous learning, you learned that when the ONU is on the internal network and the ACS is on the external network, the presence of NAT prevents the ACS from actively initiating a connection to get or set ONU parameters. So you need to configure stun. When stun does not work, for example, ACS cannot get ONU parameter, then you need to check by following step. 1. Check whether ONUTR0691 can ping to stun server IP. If it done, then check the stun username and password is correct or not. 2. Then please use Wireshark to capture the packet. Put classic stun in filter. Check whether the device sends the binding request and whether the server replies the binding response packet. Normally, the ONU sends binding requests periodically. 3. If ONU does not send request, then please check ONU configuration or contact VSOL technical supporter. If server does not reply, then please check server stun configuration or contact server provider. That's all for this course. Thank you for your attention and listening.